Good morning. Today we will discuss a topic called stability analysis of solution of finite difference equation. This is a topic in computational fluid dynamics course. Myself, I am P. Venkata Mahesh, assistant professor in mechanical engineering department, Institute of Aeronautical Engineering. Now, why we have to do the stability analysis? When we solve the finite difference equations that we derived from by applying the finite differences to the partial differential equations, there may be some errors, and these errors they may magnify or they may decay with respect to time or with respect to iterations. Now, these errors can be introduced because of two types. One is the round-off error. Round-off error in the sense we are truncating the Fourier's equation, Taylor's equation. We have a Taylor series expansion from which we got the finite difference form. And while getting the finite difference form, we have seen that there is a truncation error or the order of accuracy. Okay. Now the order of accuracy or truncation error has come because we cannot solve the infinite terms of the Taylor series in the computer, or manually also we cannot solve. So in order to reduce the effort of the computer, what we have to do, we have to truncate the equation at particular point with the required accuracy. Say suppose I want 0.0001 accuracy, then I have to take the order of accuracy of 10 power or delta x power 5. So like that, based on our requirement, we have to truncate the finite difference equation when we have to adjust with some accuracy. So that is called the round-off error because of the ability of the computer. Okay, so the computer cannot solve the infinite number of terms. So what we are doing, we are truncating the expansion, the series expansions up to some point depending on the order of accuracy that we need. So that is called the round-off error. So the other error is the discretization error. So the discretization error means we are not calculating the entire domain. We are calculating the solution at some discrete points. Okay. See, because we are not evaluating the continuous space, there will be some error, and that error is called the discretization error. So we will get this kind of errors, the round-off error and discretization error in solving the finite difference equations for the given particular problem. Now, if these errors are not controlled, what will happen is the errors will keep on growing and the solution will become unstable. Okay. Now, because of that reason, what we have to do, we have to understand how the errors increase and we have to control these errors. So that is the essential part of obtaining a successful solution using the finite difference equations. Now, in some cases, what happens is the stability analysis becomes very difficult or cumbersome. So in such cases, instead of going to the numerical analysis or finite difference analysis, it is recommended to go for the experimental analysis. Now, the stability analysis of the model equations along with the numerical experimentation should provide the limitations of time steps. So what is the meaning of this? So if I do the numerical analysis and also the stability analysis for the equations, what it will give is, while doing the numerical analysis, what should be this time step size? Say suppose delta t is the time step and delta x is the increment in the space. So this is this time step in this, this is the step size in space and this is the step size in the time. If I do the stability analysis prior to the doing the experimentation analysis, what I can do is I can decide a proper time step and proper the step size in space so that I get a stable solution for the given finite difference equation. Now, there are two methods in doing this stability analysis. One is the perturbation stability analysis. The other one is von Neumann stability analysis. So these are the two stability analysis that are generally done. The von Neumann analysis here is more commonly done, and because it is less cumbersome, because mathematically it is simpler than the discrete perturbation analysis. That is the why we generally go for the von Neumann stability analysis. Even then, the discrete perturbation analysis, okay, the discrete perturbation analysis, it will give some input, okay, it will give the graphical effect of disturbance, okay, it will give the input or it will give the insight into the effect of disturbance, how it grows with the solution. So that's why we'll do the discrete perturbation stability analysis also most of the cases. So first we'll see one by one. First we'll see the discrete perturbation stability analysis, and then we'll go for the von Neumann stability analysis. Now this is in this method, the discrete perturbation stability analysis, what we will do is we will introduce some disturbance into the solution at a particular point, and we will see its effect on the neighboring points. So that is the essence of the discrete perturbation stability analysis. What is the essence? We will introduce some disturbance at one point and we will see the effect of the disturbance on the neighboring points. So that is the analysis. Now, if the disturbance dies out or if it decays with time or if it decays as the solution progresses, then the technique, the numerical technique that we are using is a stable one. If it grows, then we call it as unstable. So for doing this, what we are doing, we are taking one parabolic equation. This is a parabolic equation, and we use this parabolic equation, partial differential equation, for doing our discrete perturbation stability analysis. Here, alpha is assumed to be constant. It is neither dependent on time or not dependent on the space. Now, this is the equation that we have taken. If I apply the finite difference method and convert this into the algebraic equation, it will be like this. Now, what kind of finite difference technique I have used here? I have used the forward difference in time. This is forward difference in time, and the central difference in space. So, the central difference in space. So what is that means? See, suppose I have a point here, I have a point here, I have a point here, and I have a point here. This is n plus 1 in time, and this is n in time, and this is I minus 1, I and I plus 1. So in space it is we are going in this direction, and in time we are going in this direction. Now if I do this FTCS, forward in time, central in space method, what I am doing is I am finding the unknown term in respect of the known terms. This is the unknown term and these are the known things. So nth time interval I have solved all the notation, all the grid point values, and I am going for the n plus 1, and if I use this FTCS, I have only one unknown, all the known terms. Say suppose if I introduce a disturbance, this epsilon, okay, if I introduce this disturbance at ith node, okay, at ith node I am introducing this disturbance, and at time is n. So in time n and node I am introducing the disturbance, how that is felt at node I and time n plus 1, that we have to see. Now the disturbance is introduced in I and n. Okay, here also I and n is there, so I am adding the disturbance here in this particular term. So disturbance is added at node I and in time n. So if I add that, what I will get? UIN. UIN is initial one. I am adding the disturbance, so it will become this. So I am substituting this value instead of UIN, and I am getting this equation. Okay. Now in this equation, what we are assuming is that at nth time, okay, at time is equal to n, at time is equal to n, at all nodes, at all I values or all nodes, the solution is 0. So this is the assumption. So we have initialized, say suppose we are taking at the first step, n is equal to 1 if you take, and we are initializing the all the nodes with a 0 value. So that is the meaning of this. So at ith node and nth time is equal to n, and ith node we have introduced one disturbance. That is the first step. The second one is we have assumed that the value of u at all i's at time n is equal to 0. That is the assumption. So if I substitute this uin equal to 0 in this equation, this will be 0, this will be 0, this will be 0, this will be 0. So I will end up with only this equation. Now if I rearrange this, delta t will go this side and this epsilon will come this side. In that case, this 2 epsilon alpha by delta square x square into delta t into epsilon. So like this it will come. If I take this e outside, okay, the epsilon outside, what will I get is 1 minus alpha into 2 delta t by delta x whole square. Now what I am doing is I am considering this, not this, the 2 I am not taking, I am taking alpha delta t by delta x square. Well, I am considering this term as the diffusion number. Okay, this entire term is termed as the diffusion number. If I use the diffusion number in this equation, what it will become? 1 minus 2d u I n plus 1 is equal to epsilon into 1 minus 2d. So this is the equation. So what I did, I have found the effect of this epsilon at u I n at, okay, I have introduced this disturbance at I n, ith node n time. Now what is the effect of it at ith node at n plus 1 time is given by this equation. Now this represents the propagation of error to grid at n plus 1th time. Okay, at ith node and at time interval n plus 1, what is the error is given by this equation. Now what I have to do? I have to prevent the growth. So the definition of the stability or stable solution is that the error should decay with time or with iterations. As the solution progresses, the error should decay. That is the meaning of the stable solution. So I have to prevent this solution or prevent the growth of error with the solution. So for that I need some condition to be applied. So what is the condition? The condition is that the absolute value of error propagation, the absolute value is set to less than or equal to 1. Okay. So here this is giving the how the error is progressing. So I am applying the modulus of this value should be less than or equal to 1. So if I apply this modulus less than or equal to 1, what is this equation? This is nothing but 1 minus 2d modulus of this is less than or equal to 1. If I apply this 1 minus 2d less than or equal to 1, here we are taking a modulus. So modulus means it is having two conditions. One is 1 minus 2d less than or equal to 1 and 1 minus 2d greater than or equal to minus 1. These are the two cases I will get. Now in the first case if I take, so this is the first case of the equation. So in the first case, what happens to the solution? So here it will be d 2d, okay, this one will get cancelled, and what I will get is I will get as minus 2d less than or equal to 0. Okay, minus 2d less than or equal to 0, or d is greater than or equal to 0. Now for all generally d is positive value, so this is satisfied for all positive values of d. So this is not imposing any condition for stability. So it is saying that for all values it is satisfied. But if I consider the second case, so what is the second case here? The second case is 1 minus 2d greater than or equal to minus 1. So if I simplify this, what it will be? 2 greater than or equal to 2d, or d less than or equal to 1. So this is the condition. So if d is less than or equal to 1, then the solution will be stable. So that is the condition that is that we are obtaining by the n plus 1th time interval term. Okay, we will see further. We will see the effect of this disturbance that we have created. We have created the disturbance. Say suppose this is 1, 2, 3, I minus 1, I plus 1, and this one is I minus 1, I and I plus 1. Or I will write it clear. If it is not clear, I will write in the form of a grid. It will be easy. So this is I am taking grid like this. So this is I, this is I minus 1, this is I and I plus 1, and this is n and n plus 1. Okay. So at n plus 1, so this is nth time step and this is n plus 1th time step, and here these are the nodes I minus 1, I plus 1. One before is I minus 1, one after is I plus 1. Now we have seen the effect of the disturbance that we have induced here at this point. What we have to do see, now we have to see at I plus 1th time and I minus 1th node, I plus 1th node, I minus 1th node, how this effect of the disturbance will be, that we have to see. So for that what I have to do, I have to discretize this FTCS for what is that, I plus 1th node. I plus 1th node I have to discretize. Then only I will get here I plus 1th node. Okay. So what I am doing here now, I am starting with I plus 1th node. Okay. If one before will be I and one after will be I plus 2. Okay. And the time, this is in time it is n and in time it is n plus 1. Now here it is I plus 1. Now what is the effect of this because of the disturbance at I, that we are going to see. So if I apply the FTCS like this, what will happen is the space, in space there is no change here, we are doing at I plus 1th node, and the time we are going forward, so it is a forward difference n plus 1 minus n. And here in this term what we are doing is we are concentrating on space and time is constant. So in space what we are doing, in space we are discretizing with a central difference. So central difference is, this is I plus 1, 1 before is I plus 2, 1 after is I. So using we'll get this kind of equation if I use the FTCS for I plus 1th node. Previously we have done for ith node what is FTCS. Now here we are doing I plus 1th node FTCS. So if I do FTCS like this, I plus 1th node and time interval I will get this equation. Now where we have introduced the disturbance at UIN. So UIN I have introduced the disturbance. So and what are the assumptions that we have taken? For all n, at time n, for all i's, the value of u is equal to 0. So if I substitute this in this equation, this will be 0, this will be 0, this will be 0, okay, and as well as this will be 0. If I apply zeros for all the cases, and already we have alpha delta t by delta x square equal to d. So this condition also we have. Now ui and I plus 1 n plus 1 is equal to alpha delta t into 2 divided by delta x square. So this will come, and into epsilon. 2 will not be there, epsilon will be there. So epsilon will be there, and epsilon alpha epsilon delta x square into delta t. So this I will get. In this I know alpha delta t by delta x square equal to d. So this is the equation. So the equation that we have got is I plus 1 n plus 1 is equal to d epsilon. So it is multiplied by d. So at u I n plus 1 the error has become reduced, e minus epsilon minus 2 epsilon d. Now at n plus 1th time and I plus 1th node, it is multiplied by d. Now we will see the disturbance at I minus 1th node. Okay. Now I minus 1th node, what I am doing? I am at I minus 1 node. Okay. 1 before means I, and 1 after is I plus 2. This is nth time. And n plus 1th time I am at I minus 1. So if I use this, using these 3 nodes, I have to find out what is I minus 1. So how to do that again? The same FTCS. In FTCS, here in time we are concerned with time n plus 1 and n. The space, it is same I minus 1. And in space, if you see, okay, in dou u square by dou x, it is derived if differentiated with respect to space, and dou u by dou t, it is differentiated with respect to time. So here we are interested in time, here we are interested in space. So what we are doing here? Alpha into uin minus 2 uin I minus 1 n and ui minus 2n. So the central difference will be forward minus 2 into the present plus the afterwards. So like this we will get. This is I minus 1. We are at I minus 1. So if 1 before means I minus 2. 1 after is I. If I add 1, I will get I. If I deduct 1, I will get I minus 2. So using that I am getting this equation. Now the disturbance that we have introduced at uin. So I introduced the disturbance here, and we have assumed that at all i's, all nodes u is equal to 0 at time interval n. So all u's are 0. So I am putting this as 0, this as 0, this as 0 at time n. So if I put like that, and this one is also 0. Now it is simplified into ui minus 1 n plus 1 is equal to alpha delta t by delta x square into epsilon. Now again this is equal to d that we have already taken assumed. So it is becoming like this. So at I minus 1 node and I plus 1 node, at time n plus 1, it is remaining same and it is equal to d into epsilon. Now we will see at another node n plus 1th time. Okay, so far we have seen n plus 1th time we have seen. Now we will see n plus 2 time. So what is the time? Time is between n plus 2 and n plus 1. But space coordinates we are looking at I. So this is I. 1 before is I minus 1. 1 after is I plus 1. So the space is between I minus 1 and I plus 1. And the time is between n plus 1 and n plus 2. So if I use the FTCS for this kind of these nodes, if I use the FTCS, it will be like this. Now in this equation, we know what is ui n plus 1. Ui n plus 1 is equal to epsilon into 1 minus 2d. And I know what is ui plus 1 n plus 1. It is a dE. ui minus 1 n plus 1 is also known, that is a this d into epsilon. So if I substitute all these values into this equation, what I will get? I will get epsilon into 1 minus 2d. Why we will get epsilon into 1 minus 2d? You see here, this is ui n plus 1. Ui n plus 1 is epsilon into 1 minus 2d. I substituted that value. And here ui plus 1 n plus 1. Ui plus 1 n plus 1 is d into epsilon. I substituted that one here. And ui n plus 1 is epsilon into 1 minus 2d. I substituted that one here. And ui minus 1 n plus 1 is d epsilon, that I substituted here. Now if I simplify this, what will happen? See here, epsilon, epsilon, epsilon. Everywhere epsilon is there. Epsilon I have taken outside. Now here it is 1 minus 2d, and here it is d square. This is 1, this is 1. So here d square is there. D square minus 2 plus 4d, and here what is this? This is again d square. Two minus 1 second. So this is a d square. This is correct. Minus d into 2 into 1. So it is a minus 2d, and d into 2 into 2, 4d. So it is a plus 4d square, and again here I am having d square. So d square plus 4d square, it is 6d square, and minus 2d is 4d minus 4d, and 1 is there. Like this it will be simplified. After simplification, we have to impose the condition for stability. So the condition for stability is ui plus I n plus 2 by epsilon must be less than, the modulus of this must be less than or equal to 1. So in this case again, the modulus of 1 minus 4d plus 6d square must be less than or equal to 1. Again I will have two cases here. One case is 1 minus 4d, okay, plus 6d square less than or equal to 1. The other one is 1 minus 4d plus 6d square greater than or equal to minus 1. Okay, so this modulus we have applied, so inside term can be positive or negative. So in this way it will come like this. So we'll see one by one what is the effect of these two cases. Now 1 minus 4d plus d square is less than 1. So in this case what is happening? This is my 1 will get cancelled, and it will become 2d minus 2d 3d square. 3d square minus 2d less than or equal to 0. Okay, 3 3d square minus 2d less than or equal to 0. Now what is happening, if I so the d is always positive, so this is not the case. So if d is always positive, so it will be 3d less than or equal to 2d, so less than or equal to 2. Now d is less than or equal to 2 by 3. So this is the condition that we are getting. So the d value must be less than or equal to 2 by 3 for this equation to be stable. At which location we got? We got as at n plus 2. At n plus 1, the d must be less than or equal to 1. Now it is less than or equal to 2 by 3. So it is less than 1. So it is decreasing. The stability, the criteria is getting reduced. Now if I take the other case where 1 minus 4d plus 6d square is greater than or equal to minus 1. Okay. So if this is the case, what will happen? It will become 3d square minus 2d is greater than or equal to 1. There is a mistake here. It is this 2 will go this side. So it is 2 minus, I'll write here, 2 minus 4d plus 6d square greater than or equal to 0. Okay. So if I simplify this, it will be 1 minus 2d plus 6, it is 3d. 3d square is greater than or equal to 0. Now what happens if I bring, if I apply minus sign here, what will happen? It will become, I am bringing these terms this side. Okay. If I bring all these terms this side, what will happen? 3d square minus 2d must be so if I apply minus here, this is minus, this is plus, and this will become minus. And what happens to this sign? It will become less than or equal to 0. Now what I am doing, I am bringing these two terms this side. So it will be minus 1 less than or equal to 3d square minus 2d. So like this it will become. Now in this case, for all values of d, whatever d we may put, it will be greater than or equal to minus 1. So this is the, this condition is not applying, imposing any stability criteria, but because for all values of d, it is satisfied. So we are interested only in one criteria, that is this one, and it is imposing a restriction that the d value must be less than or equal to 2 by 3. Now the analysis we have seen for n plus 1, n plus 2, like that. So we can go to higher levels and find out what is the restriction on d that is to be imposed for stability criteria. Now as it progresses, what happens is, after some time the error will become same in magnitude. Okay, same magnitude will come, but same magnitude will have two possibilities. One is, even though it is same in magnitude, the sign also will be same, and the other case is the size, magnitude is same but the sign is opposite. One is plus, the opposite other one is minus. So in that case we will see what happens. So we have reached up to a time m where the magnitude of the error is same. The error is e power m. Okay, at mth time, error at time m is equal to epsilon. Okay, at time m the error is same for all the nodes, but here the first case the sign is also same. If I take the sign is also same and substitute this in the FTCS equation, what will happen is ui m plus 1 is also equal to e epsilon power m. So what is happening? Before in mth at a time is equal to m, the error is epsilon power m, and at a time m plus 1 also, the epsilon power m is it is retained. So it is not decaying. So this is not a restriction condition. The stability criteria is not satisfied. Now we will see the other one where the signs are opposite. So at I minus 1th location it is minus, at ith location it is plus, and I plus 1 location it is minus. So the sign is alternating. So in this case what is happening is, if I substitute these values into our FTCS equation, what is happening here? This is minus, this is e power m. I am substituting that one here, and this is e minus epsilon power m, and this is minus epsilon power m. If I substitute all these equations and if I simplify this, what will happen? Alpha delta t by x square. Okay, alpha delta t by x square, delta x square. Alpha delta t by delta x square is nothing but d. And here what is happening here? It is minus e power minus epsilon power n minus 2 epsilon power n minus epsilon power m. So it is minus 4 epsilon power m. Okay, and here it is epsilon power m. If I bring that one here, I will get epsilon power m, positive one. So, and what else I am getting? I am getting alpha into delta t into divided by delta x square. So that will be included as d. So how it is simplifying? It is simplifying as 1 minus 4d into epsilon power m. Okay. Now this is the equation. Now again we have to impose a stability criteria. The stability criteria, as we have done previously, it is same as ui m plus 1 by epsilon must be less than or equal to, modulus of this must be less than or equal to 1. If I apply this, again I will have two cases. One is a positive one, one is a negative one. So what is that? It is 1 minus 4d, modulus of this is less than or equal to 1. The first case is 1 minus 4d less than or equal to 1. The second case is 1 minus 4d is greater than or equal to minus 1. Now if I apply this condition, what is happening is this will go, this will go. So the 4d must be greater than or equal to 0. The 4d must be greater than or equal to 0 means it is satisfied. The d value is positive. So for all values of d it is greater than 0. So this is not imposing any restriction here. So the other condition we will see. The other condition is 1 minus 4d is greater than or equal to minus 1. If I impose this one, it is 2 greater than or equal to 4d or d less than or equal to half 2 by 4 or 1 by 2. So we have reached a case where the d is less than or equal to half, then only the condition is stable. Okay, the solution will be stable. Now we will see, so we will take some particular values of this and we will see how it will be there. Now if I take d, okay, now what we got? The solution will be stable when d is equal to less than or equal to half. Okay, we have taken a disturbance. Okay, we have taken a disturbance. It is growing. So when it will decay? When d is less than or equal to half. So if I take a d value of 0.25, so what is half means? It is 5. So some less than value of d we are taking a 0.25, and if I calculate these values for d, what is d? D is a alpha delta t by delta x square. This is a d. I am taking d value as 0.25 and I am using that in the deciding what is time step. What is time step? For the particular value of the nodal distance or the size, the node value, the grid size value. For for a particular delta x value, what should be the delta t value? We are deciding by this, and when we take 0 t d is equal to 0.25, the error, initially the error will be this much. At n plus 1th node it will reduce, at n plus 2th node it is further reduced, so further like that it will go on decay. Say suppose if I take a value greater than equal to 0.5, so I am taking a value of 1.5. If I take 1.5, what will be the delta t? Delta t is equal to, so the d is equal to 1.5 I am taking. So if I take d is equal to 1.5, alpha delta t by delta x square is equal to 1.5. So if I take this one this side, it will be delta x whole square, and alpha will be here, so divided by alpha. So for a given delta t value, for a given delta x value, I am taking a delta t value from this relation, and if I take this relation, what is happening to the error is, the error is fluctuating, it is increasing and fluctuating, so it is not a stable solution. So this is the discrete perturbation stability analysis. So what is happening, if d is less than 0.5, the solution is stable. If d is greater than 0.5, the solution is not stable. Okay, so how we arrived here? We have taken at nth node, n plus 1th node, we got that d should be less than or equal to 1, and after that we got d is less than or equal to 2 by 3, and we have further we have seen, and at a particular location the condition is that d is less than or equal to half, where the error has become equal, all the nodes. Okay, so using that stability criteria, we have seen that if d is less than half, the solution is stable. If it is greater than half, we have taken, and the solution is not stable.
Like, share and subscribe. Hit the bell icon for more updates.